Now we turn to deletion. This is the trickiest operation because removing a node must keep the whole tree ordered. Deleting a node must keep the tree ordered. What that takes depends on how many children the node has. There are three cases. Case 1. The node is a leaf with no children. You free it and its parent's link becomes nil. That is the easy case. Case 2. The node has exactly one child. You free it and its parent links straight to that one child. Case 3. The node has two children. You copy up the inorder successor's key, then delete that successor from the right subtree. So what exactly is the inorder successor? For a two-child node, it is the smallest key in that node's right subtree. You find it by going to the right child, then walking left and left again until there is no more left child. That successor has at most one child of its own, so removing it is always a case 1 or a case 2 delete. Note it may sit several levels down, not just one. And that is what lets you solve case 3 by recursing, instead of splicing pointers by hand. Now the trap. You might think a two-child node can be replaced by either of its children. It cannot. Moving a child straight up usually breaks the ordering against the other subtree. There are exactly two safe replacements, and they are the node's inorder neighbors. The successor, which is the smallest key on the right, or the predecessor, the largest on the left. We use the successor throughout this course. The reason it is safe is that the successor is larger than everything on the left and smaller than everything else on the right. It slots in without disturbing either side. Deleting a leaf is the easy case. The left figure shows the tree before we delete. We want to remove the key 4, shown in red. 4 has no children at all. Now the tree after. We simply cut 4 away. Its parent 6 had a left link pointing at 4. That link now becomes nil, which means empty. Nothing else in the tree changes. Here is case 1 in code. This line is the test. We check whether root arrow left is null and root arrow right is null. If both children are empty, the node is a leaf. We free the node. That gives its memory back so nothing leaks. Then we return null. Because the caller stores what we return, the parent's link now holds null, and the leaf is gone. Removing the leaf itself is big, O of 1, one quick step. But first we had to find the victim, and that walk down the tree is big, O of H, the same as an ordinary search. Now the victim has one child. On the left we want to remove 6, shown in red. 6 has lost its left child from the last step, so it has only the right child, 7. Now the result. We lift the one child up into the victim's place. 3 used to point at 6. Now 3 points straight at 7, shown in green. 6 is gone, and the rest of the tree is untouched. This line handles the case where root arrow left is null, so the node has only a right child. We save the one child in a pointer called child. We free the victim node, so its memory is returned. We return that child. The parent now points straight at it. The comment on the last line reminds us there is a matching branch for a node that has only a left child. Your turn. A node has a null left pointer and a real right pointer. Which delete case is this, and what takes the node's place? Pause for a moment. The answer is case 2, one child. The node's right child moves straight up in its place, and no successor search is needed. The symmetric branch handles the node that has only a left child. This is the hard case and the most important one. This is the tree before we delete. 10 is the victim, shown in red. 10 has 2 children, so we cannot just cut it out. We need one key that can safely sit in its place. That key is the inorder successor. It is the smallest key in the right subtree. So we go right into the subtree and start at 14. From 14 we keep going left. We reach 13. 13 has no left child, so we stop. 13 is the successor. It is bigger than everything on the left and smaller than everything else on the right, so it is safe to move up. Now we copy the key up. The victim node keeps its place in the tree, but its key becomes 13, shown in green. Its children, 9 and 14, do not move. But look down here. The old 13 node is still in the tree. We copied the key, but we have not removed its source yet. This is exactly the step a careless delete forgets to finish. So we finish it. We delete the old 13 from the right subtree. Down there, 13 is a leaf, so this is just case 1 again. 14's left link becomes nil, and the old 13 node is freed. The tree is correct again. 13 sits where 10 used to be. Every key on the left is still smaller, and every key on the right is still larger. Notice how we removed the successor. We called the same delete function again, 1 level down. That recursion does the pointer work for us. Here is a quick check on what you just watched. Which single key moved up to replace 10, and why was it the only safe choice? Pause and answer. The key is 13, the inorder successor, the smallest key in 10's right subtree. It is larger than everything on the left and smaller than everything else on the right, so both subtrees stay ordered when it moves up. Let us write the two-child case as a plan, before the C read it line by line. Y becomes the minimum of X's right subtree, which is the successor. Then X's key becomes Y's key, the copy up. Then X's right subtree becomes the result of deleting Y's key from it, which is the step that actually removes the old node. Then return X 4 lines, and this is the pointer mutation students most often get wrong. The right side is the real C we make a pointer called successor. We set it to the minimum of root arrow right, which is the smallest key in the right subtree. We overwrite the victim's key. Root arrow data becomes successor arrow data. The victim node stays, but now it holds the successor's key. This is the line students most often forget. We set root arrow right to the result of deleting the successor's key from the right subtree. That call removes the old node and frees it. We return root, so the parent keeps pointing at this fixed subtree. The cost is big O of H to find the successor, plus big O of H to delete it. Added together, that is still big O of H overall. Let's see the two-child delete on one page. From the idea, to the pseudocode, to the C. This is the operation students most often confuse with what actually changes in memory. Step 1. Find the smallest key in the right subtree, the inorder successor. It is always safe to move up, because it is bigger than everything on the left and smaller than everything else on the right. In C that is, successor equals the min of root arrow right. Step 2. Overwrite the victim's key with the successor's key. The victim node survives. Only the key moves. In C, root arrow data becomes successor arrow data. And step 3, which needs a slide of its own. Now remove the successor node itself from the right subtree. Its key is a duplicate down there now, so the node must actually be unlinked and freed. In pseudocode, X's right becomes delete of X's right and Y's key. In C, root arrow right becomes BST delete of root arrow right and successor arrow data. Skip that third row and you have copied a key, but never removed its source. The old successor node stays in the tree, holding the same key that now also sits at the victim's old spawn. The tree has a duplicate it was never supposed to have. That is exactly the bug in common mistakes, which is next. Finding the minimum and the maximum is the same idea as search, but with no comparisons. You just keep going one direction until there is nowhere left to go. Your turn. In the chapter's tree with root 8, which node holds the smallest key and which one direction do you walk to reach it? Think about it, then read the code. The min function walks to the leftmost node. In a search tree, the smallest key is always at the far left. First the guard. On an empty tree there is no minimum, so we return null. This loop does all the work. While root arrow left is not null, we move root to root arrow left, so we keep stepping left until the left link is empty. And that last node is the minimum. Notice there are no key comparisons at all here. The ordering rule already tells us which way to go. Max is the same idea in reverse. It walks to the rightmost node, because the largest key is always at the far right. Here we step right instead. While root arrow right is not null, we move root to root arrow right until the right link is empty. Min and max each cost big O of h, one straight walk down a single side. Inorder still costs big O of n because it visits every node once. And on a search tree, inorder prints the keys in sorted order. That comes free as a side effect of the ordering rule.